So now that you have an intuitive grasp of sensitivity and specificity, we're going to show you how to actually calculate sensitivity and specificity. So this depicts 20 individuals, 7 of whom have a disease and the rest do not have the disease. The diseased people have the red dots on their heads. Then we do a blood test to determine who has the disease and who doesn't. The blue circles indicate positive test results. So what this shows is that of the 7 people with the disease, the test said that 6 of those were positive. So the test accurately captured the disease in 6 out of 7. And then of the 13 people who did not have the disease, the test said 2 of those were positive. So it was accurate in 11 out of the 13. So this is the table that we use to calculate sensitivity and specificity. So it's a 2x2 table, and then the first column we put all the people with the disease, second column people without the disease, first row the positive test results, and second row the negative test results. So now we'll put the 20 figures from the prior slide into their appropriate locations on this grid. So now we've put the true positives in their location. So these are people with the disease with a positive test result. And then the false negatives here. So this is a person with the disease but with a negative test result. And now we have the people, all of whom did not have the disease, but 2 of those without the disease tested positive, so those are false positives, and then 11 appropriately tested negative. So let's calculate sensitivity. Sensitivity is the accuracy of the test at finding the people that have the disease. So it's the extent to which the test is positive in people with the disease. So over here we have our 7 people from the original 20 people who have the disease. So what proportion of those people tested positive for the disease? So as we saw before, 6 out of those 7 tested positive on our test. So now we'll put those numbers into our grid. So what we have here are the true, we're just again focusing on the people with the disease for sensitivity. And we've got, out of 7 total people, we have 6 who tested positive, and we have 1 who tested negative. So the sensitivity of the test is, again, the proportion of people who have the disease that tested positive. So that would be the true positives over all of the people with the disease, which is the true positives plus the false negatives. And so in our case, that would be 6 over 6 plus 1, or 6 sevenths. 6 sevenths equals 0.86, which you could say is 86%. So the sensitivity of this test is 86%, meaning 86% of the people with the disease were tested positive. So a test needs to be sensitive, that is, it needs to be able to identify the people who do have the disease, but it also needs to be specific and only give a positive result to the people that have the disease and give a negative result to the people who do not have the disease. So it has to correctly identify the people without the disease. So specificity is focusing on those people without the disease and how accurate the test is for those people without the disease. So over here are the people, the 13 people who did not have the disease from our original 20 people. And when we tested them, we found that 2 of those people tested positive. So we'll put the numbers into the table. So we have, for false positives, we have 2. And for true negatives, we have 11. So the specificity is the proportion of test results that were accurate among people without the disease. So therefore, specificity equals the true negatives, which is the accurate number of accurate test results, over all of the people without the disease, which would be the false positives plus the true negatives. And so in this case, we have 11 true negatives over the total number of diseased is the false positives plus the true negatives, which equals 11 over 13, which, as you can see over here, is just literally the proportion of the non-diseased who had an accurate test result. So this equals 0.85, which equals 85%. So what that says is there's a specificity of 85%, meaning that among the non-diseased, 85% of the test results were accurate, meaning they were negative. So how would knowing the sensitivity and specificity of a disease help you in clinical practice? Well, as you probably know, there are these mnemonics. So for sensitivity, the mnemonic is snout. And what this means is that for a sensitive test, a negative result rules out the disease. And so how can we see that in the table? So if we imagine a test that has 100% sensitivity, so that means that 100 of the people with the disease have a positive test and no one has a negative test. Okay, and let's just say the specificity is lower. Let's say the specificity is 70%. So that means out of 100 patients, again, 70 will have an accurate test result, meaning that's a true negative, and 30 will have a false positive. So what that means is, let's just pretend that you're doing using this test to diagnose a disease, and so you get a positive result. Okay, so that means that it doesn't mean that it doesn't assure you that the person has the disease, because for this test, given the lower specificity, there is a chance that the positive test result will be false. Okay, because 30% of the time, people without the disease have a positive test result. However, if you get a negative result on this test that's highly sensitive, okay, a negative result, then you can be sure that the person does not have the disease, because if it's a very sensitive test, let's say it's a 100% sensitive test, then there is no possibility of this person having a negative test and having the disease, because there are no false negatives. And that's because the false negatives are inversely proportional to the true positives. So that's why if you have a highly sensitive test, a negative result rules out the disease, because there are no false negatives. So similarly, for specificity, the mnemonic is spin. And so what this means is that for a specific test, a positive result rules in the disease. So using a similar scenario to what we just used for sensitivity, just imagining that, let's imagine that we have a highly specific test, and for now we can just say that it's perfectly specific. So that means that, let's say 100, we have 200 patients, 100 patients have the disease, 100 patients do not have the disease. And so our test is 100% specific, so that means that there's 100 true negatives and no false positives. So it's perfectly accurate at ruling out the disease, at determining who does not have the disease. And then the specificity, let's just say, is a little bit is lower. So we can say the sensitivity is lower. So we can say the sensitivity is 70%. So we have, again, of the 100 patients with the disease, 70 test positive and 30 test negative. So what we can say here is, okay, so we're doing a test, and in this case, this test is highly specific, okay? And so we get a positive result, okay? As it says here in the mnemonic, get a positive result. So because if the more specific the test is, and in this case it's 100%, but even if it's a little bit lower, the likelihood of false positives is very low. Again, inversely proportionate to the true negatives. So if you get a positive result, then you know it's very unlikely to be false. Okay, so therefore it's likely to be true. So it rules in the disease. So in sum, the most informative outcome on a highly specific test is a positive result, okay? And the most informative outcome on a highly sensitive test is a negative result.